Mathematical induction, we shall show how to prove this theorem. 2 times n is less than or equal to 2 raised to n, where n is a positive integer. We shall show that this is true using mathematical induction. So this is the organization of our proof if we were to prove a proposition using mathematical induction. So this is the challenge. Prove that for any positive integer n, 2 times n is less than or equal to 2 raised to n. We begin by stating the proposition. So when we have not yet proven it, we call it a proposition. So for any positive integer n, the proposition is 2 times n is less than or equal to 2 raised to n. We begin our proof. The first part of our proof is the base case. Let us show that the proposition is true for the initial values of your n, for n is equal to 1, 2, and 3. Well, when n is 1, 2 times 1 is less than or equal to 2. That is true. When n is equal to 2, 2 times 2 is less than or equal to 2 squared. That again is true. When n is 3, 2 times 3 is 6, and 2 cubed is 8, and 6 is less than or equal to 8. That is true. So we are done with the base case. We now proceed with the inductive hypothesis. So what do you do at the second part of the proof using mathematical induction? Well, you are going to make a tentative assumption that the proposition is true for any positive integer k. So be sure to change your dummy variable. You must use a different variable here, k. And your goal is to show that this will imply that the proposition is also true for the next integer after k, and that is k plus 1. 2 times the quantity k plus 1 is equal to 2k plus 2. Look at this. 2k plus 2 is less than or equal to 2 raised to k plus 2. Now, why is this true? Well, look at this. 2k is less than or equal to 2 raised to k. We are supported by our inductive hypothesis. This is our hypothesis. This is our temporary assumption. And so we are right to make the claim that 2k is less than or equal to 2 raised to k. Now, using addition property of equality, we are adding 2 to both of those terms. Then, this inequality is true. 2k plus 2 is less than or equal to 2 raised to k plus 2. For any positive integer k, 2 is less than or equal to 2k. This means that 2 raised to k plus 2 is less than or equal to 2 raised to k plus 2 raised to k. Okay, so why are we justified in making this statement? Well, 2 raised to k is less than or equal to 2 raised to k. That is true. But this one, 2 is less than or equal to 2 raised to k. So that is like the addition property again of inequality. Now, what is this? 2 raised to k plus 2 raised to k is 2 times 2 raised to k, and it is equal to 2 raised to k plus 1. This is just loss of exponents. So here again, I am emphasizing we are applying the addition property of inequality. By the transitive property of inequality and by the statement 1 and 2, 2 times k plus 1 is less than or equal to 2 raised to k plus 1. Now look at this. 2 raised to k plus 2 is less than or equal to 2 raised to k plus 1. Okay, so that comes from your statement here labeled as number 2. And that is also the application of your transitive property of inequality. 2 times k plus 2 is less than or equal to 2 raised to k plus 2. That's our statement number 1. That is in the previous slide. Our statement 2 is 2 raised to k plus 2 is less than or equal to 2 raised to k plus 2 raised to k, which is the same as 2 raised to k plus 1. This is just the application of the laws of exponents. So combining these two, the transitive property of inequality and statements 1 and 2, we now conclude that 2 raised to k plus 2, which is the same as this, is less than or equal to 2 raised to k plus 1. So we have shown it. We have shown it. When we assume that the statement is true for k, we were able to show that the statement is also true for the next integer after k, which is k plus 1. Conclusion, for any positive integer n, 2 times n is less than or equal to 2 raised to n.